Welcome to the Faculty of Civil Engineering, University of Transport and Communication, Hanoi, Vietnam. I would like to introduce Mr. Andreas Schwartz from VSL International today to come to university to present a topic about bridge repair. So he will show the experience he have in many projects around the world. So let's you to talk now, and then we have questions.
Very good.
Thank you very much.
Thank you very much for having me today. So it's my pleasure to talk about bridge repair and preservation. I want to start off with a bit of an introduction about the role of specialist contractors when it comes to repair and preservation. VSL is a specialist contractor operating worldwide, and we try to bring really fully integrated specialist construction services to the existing bridges market to repair, strengthen or upgrade existing bridges. So we see that this requires the combination of good design and engineering with specialist systems and technologies and the ability to execute these works in a safe, professional and cost-effective manner. So it all starts with thorough inspections of existing structures, because obviously different to new build structures, on existing structures we normally do not know the condition of the structure right from the start. So it starts with good inspection. Our approach, and I think the approach that has worked well on a lot of structures that we were involved with worldwide, is a thorough desk study to start off with, to understand the structure, understand the structural system and the structural behavior, to identify critical elements and systems, for example, bearings or cables supporting the bridge deck, to identify particular risk areas, and finally to analyze all the constraints that we might have to access the structure, to work on the structure and the associated health and safety risks. We can then supplement that desk study, obviously, with visual inspection on site, which tells us typically a lot about the condition of the structure. And then we can combine this with non-destructive testing technologies. Now, say here, we need to make smart use of these systems. We need to use them to establish a global risk mapping of the structure, to detect certain pathologies and damages, to visualize them, and to confirm, therefore, which are the critical areas for intervention. And I think here it's very important. There's a lot of non-destructive testing technology out there. We need to really know which ones are reliable and which ones have a proven track record to deliver the right results. And finally, we combine this very often with some level of intrusive inspections. So either in order to get direct visual confirmation of some damage to the structure, we can do material sampling, for example, if we don't know the concrete strength or the steel characteristics. But this is really something we should limit to these areas where it's really needed. And we need to think from the start, how do we make these areas good again? Because if you take, for example, a concrete sample in a bridge deck, which is otherwise in good condition, you might create an area of weakness where maybe you get water in, and then you can cause corrosion over time. So it needs to be well planned. And I think this is also where it's very important that experienced specialists are tasked with doing these works. I want to show some more advanced technologies that we use quite a bit. One is the risk mapping using georadar. Georadar as such, I think, is a well-known technology and a well-proven technology, which obviously use the principle that a radar wave gets reflected by any steel object in the structure, and you can use it to locate reinforcement steel or post-tensioning tendons. But by calibrating it with the actual characteristics of the concrete and the concrete cover zone, we can also use it to produce damage maps. And these damage maps can give you an indication of corrosion risk, because the response of the radar signal is linked to the ion concentration in the concrete and therefore to the concentration of chlorides or humidity. And in top of that, you get the information about concrete cover thickness or areas of delamination, for example, between the asphalt and the concrete, or where you have a waterproofing. So it's a very good method to get very quickly a good overview over the condition of a bridge deck and to identify hotspots of deterioration. You see here on the left a picture of one of our staff walking a bridge deck with a scanner. So it's a very simple intervention that can be done while the asphalt is still on the bridge and gives you very quickly a good overall understanding. We have also some advanced technology-enhanced solutions to inspect particularly post-tensioned structures. So with post-tensioned structures, whether they are pre-tensioned or post-tensioned, we need to understand there are certain external risks that can jeopardize the durability of the bridge, and we have some internal risks. The external risks is conventional corrosion in the reinforced concrete due to carbonation or the introduction of chlorides in marine environments, for example, or corrosion of exposed anchorage components of the systems. But we also know today that we have some internal risks. They can come from water infiltration into the structure, for example, due to bad detailing of drainage systems, the absence of waterproofing membranes, or cracks in the structure. And inside the tenons, we have also understood today there are certain phenomena that can cause highly aggressive conditions. This can be the bleed of grouts during grouting initially, that can result in segregation of the grout material, like you see in the photo in the bottom left with the red patch here, where we have opened the duct of an external tenon, and instead of finding good solid gray grout, we find this white paste, which is actually very moist and has a high level of sulfates, and then can cause very accelerated corrosion. So we have today also non-destructive testing solutions, like you see in the bottom right. This is an electrical capacitance tomograph, which allows us to scan such tenons and identify those areas, hopefully before damage is caused. On other structural elements that are very important for a lot of bridges, and particularly also here in Vietnam, you have a lot of cable stayed bridges. We're able today to do some robotic inspections. You see here a camera robot that we use to climb up the cable to record a full 360-degree image of the cable surface. And then what you see in the bottom right is actually a computer vision algorithm based on AI principles that we use to post-process this data to automatically detect and classify the damages. So instead of an engineering having to look through hundreds and hundreds of hours of video feed, we let the computer do the work for us, and then we end up with a list of classified defects which can then be reviewed by an expert to decide on the course of action. This is, for example, important because we have on our stay cables certain aerodynamic features, either helical ribs or in some systems dimples, where it's important that they function over time, and this can, for example, be verified by visual inspection, or also the absence of holes or damages to the cables. Now this is as far as inspection goes. And obviously, once we have inspected a structure and we've found some damage, we need to decide what we can do in order to repair or strengthen the bridge. So there's a number of specialist solutions, and we have limited time today, so I just want to touch on a few and explain a little bit on what can be done. So here you see the picture of a bridge which we had the opportunity to work on in the UK a few years ago, which actually required a global strengthening because of some advanced corrosion of existing post-tensioning tenons in a 50-year-old bridge. And we deployed a lot of these specialist solutions to this project. First of all, we need to get access to the structure. And this might sound easy, you put a scaffold up, but very often it's not so easy because bridges are typically under traffic. We cannot close the traffic when we intervene on them, so we need to come up with some smart systems to access the bridge. You see on the image at the bottom left, for example, a project in France where we decided to bring all the equipment we needed and the whole site setup in on barges under the bridge, and we actually lifted up the barges in order to create a working platform. But other temporary works we need are things like formworks, if we need to do section enlargements, or we have checking systems or strength checking systems, for example, when we need to move heavy loads, or like you see in the picture at the bottom, this is the replacement of a vertical hanger in an arch bridge where we need to put in a temporary system to carry the load while we do the replacement. So specialist temporary works are a very important element of such interventions. Then we have different ways of strengthening a bridge. We might have to strengthen the bridge either because we have increased loading, so for example heavier trucks crossing over a bridge, or adding a traffic lane to an existing bridge, or it can be we want to strengthen in order to substitute steel cross-section, either passive reinforcement or pre-stressing steel cross-section because of corrosion. So what can we do? We can use passive strengthening systems. The most known ones are certainly composite materials, so carbon fiber or other composite fibers, which we can glue onto the structure in form of laminates or strips. We can also use bonded steel strips, or we can create a conventional section enlargement by adding additional concrete with reinforcement. Now, all these systems can be very useful, but we need to understand these are passive strengthening systems. That means in order to activate them, we need additional deformation of the structure, and we cannot control, therefore, deformations as tightly as we would like to sometimes, and it also allows us to strengthen for additional loads. If we have to strengthen for permanent loads, so for example for the structural self-weight already, or if we need to control deformations more tightly, or if we need to control cracking of the structure, the better solution is to do what we call an active strengthening. So this is adding additional post-tensioning to the outside of the bridge, and you see here a couple of photos of different systems. So here there's quite a number of variations that we can use in terms of what type of tenon we use, what type of anchorage we use. It can go from a small single or dual strand system that we anchor by coring a hole into the structure and inserting a pin, to very large multi-strand tendons where we use typically cast in situ concrete blocks or blisters, like we call them, to bring the forces into the structure. So bending strengthening is very often something that is required. But at the same time, older structures in particular suffer shear deficiencies. Especially precast beams, where often in the past, under the old design codes, the need for shear reinforcement was maybe not understood as much as it is today. So here we have a number of solutions we can apply. We can apply, again, composite systems, carbon fiber, for example, but we can also bond steel plates, or we can install post-drilled steel rods. But as with the bending strengthening, we can also take full benefit of post-tensioning. If we apply post-tensioning with inclined tendons, we can get quite a significant shear contribution, and that's again a very nice way of applying shear strengthening to a structure as well. Another typical strengthening is around the column and the pier heads, where it's often more about jacketing, confinement, and often we have to deal with durability issues here, because, for example, we can be in the splash zone near the sea, or we can have, as a typical deficiency in the pier heads, we need to apply additional transverse strengthening because we have increased loading or increased eccentricities. Then allow me to touch also briefly on the topic of post-tensioning repair and preservation. A lot of the bridges, obviously especially the long span bridges, have internal post-tensioning or external post-tensioning. And over the years, post-tensioning technology has evolved a lot. If we go back 20, 30 years, some of the durability concerns, in particular related to the quality of the grout that we use to inject these cables, have not been as well as understood as they are today. And a lot of the older practices and codes were not up to the standard that we would like to see today in terms of durability. So it means we go often to structures, we find voids in post-tensioning tendons, we find low quality grouts, both on internal as well as external tendons. And then first of all, we need to use non-destructive testing to find them, but once we have found them, what can we do? We can do, for example, vacuum-assisted regrouting, like you see in the picture on the right, which we can do by accessing the tendon along the length, or we can access the anchorages like you see at the bottom of the left. But for external tendons, sometimes you need to replace them because you have advanced corrosion, and obviously the structure not being, the tendon not being bonded to the structure means you need to control very carefully the forces and the energy when you release these tendons. And this is where controlled detensioning methods, like you see in this picture here with hydraulic checks, can be a useful solution. There's also quite a number of specialist techniques when it comes to other cable supported structures, in particular cable stayed structures or suspended structures. So this ranges from, if I go from left to right, from retrofitting, in some instances, fire protection, because the bridge is close to, the cable is close to traffic, and there's a concern about damage to the cables by fire, so we can add lightweight fire protection. We can replace entire cables when they are either corroded or suffered fatigue damage, or when we need to increase the capacity of a bridge by upgrading the size of the cables. And again here, controlled detensioning, like you see with our blue checks here in the middle, is essential. And then we have all sorts of other interventions on cables, including restressing using hydraulic checks that might be required. So this is about, let's say, general solutions for bridges. So we also need to look at these elements of a bridge which typically have a shorter design life than the bridge itself. And this is typically bearings and joints. Bearings might have a design life of maybe 30 years and the bridge might have a design life of 100 years. So a bearing is something that needs to be replaced at some stage along the life of a bridge. And if they're badly installed or if they're low quality products, that replacement might come much earlier. So here it's again about the combination of engineering, temporary works, and using the right products. There's a lot we can do. In the best case, we have enough space on top of a pierhead to put hydraulic checking equipment to be able to lift the bridge to replace the bearing. And if that's not the case, we might need to apply temporary steelworks, temporary works to create these checking points. Also very important is when we lift up a bridge, typically the bridge remains open to traffic, so we cannot just check up the bridge deck, but we need to control forces and displacements within very tight tolerances, for which we need to use synchronized checking systems. There's one picture on the bottom right which is a bit special. That's actually not a bridge, it's a building that had to be lowered, and you see here the whole building was transferred on an underpinning scheme with hydraulic checks, and the same hydraulic control systems that we can use for checking multiple points on the bridge have been used here. So it's just to illustrate what you can do with synchronized computer controlled checking systems. As I said, expansion joints is also an item that requires frequent replacement. The typical scenario is the joint fails. It first causes maybe noise, reduces the user comfort, but eventually becomes a risk because parts of the joint become loose. So you're going to have to go in and replace them. This means you need to close at least one lane for traffic, and you want to keep these closure times as short as possible. And there's today a number of different joint solutions, and one that I'm showing here is a particularly interesting one which works well for joints maybe up to a movement range of 100 millimeters, which are cast in situ steel reinforced polymeric plug joints. So this is a joint, it looks like an asphaltic plug joint when it's finished, but it's actually a high performance polymer with this spring type reinforcement inside, which allows you to use it for quite large movement ranges. And the big advantage of these joints is they are completely waterproof because they bond to the adjacent asphalt. They are low maintenance because you have no open joint gaps, and they're also low noise, which is in a lot of countries becoming more and more a topic when you are in inner city environments. Now, moving away from particular structural components, it's also interesting to look at the type of durability and resilience improvements we can bring to structures when we do repairs. So again, a large range of possible solutions. It goes from jacketing of columns with fiberglass jacketing or cathodic protection, but we can also use high performance material, and one that I will focus on a little bit more on the next slide is ultra high performance fiber reinforced cementitious products, or UHPFRCs, UHPCs like people call it, which are extremely dense and almost watertight cementitious material with a high concentration of short steel fibers, and therefore able to bridge cracks, and actually with quite a significant tensile capacity. So using this as an overlay allows you to do this type of durability repair, like you see at the bottom right, which is actually a pylon of a cable-stayed bridge that suffered alkali sulfate and alkali aggregate reaction, and it was decided to install a durability jacket using such a UHP-FRC solution. You see in the picture in the middle what it looks like. On the left, you see a surface of a bridge deck prepared by hydrodemolition or high-pressure water jetting. And on the right, you see the applied UHP-FRC material. In the dark zone, you see a bit the steel fibers. So a thin overlay as a waterproof durability layer. So you can basically apply directly the asphalt on top without additional waterproofing. And at the same time, because it's a very high strength material, it provides additional strength to the bridge deck. So it's a nice combination of combining strengthening with durability improvement. So all these solutions that I've presented allow for really novel solutions when it comes to strengthening or repairing aging assets. And I want to close with this slide here, which is a bridge in France built by the company of Gustave Eiffel. And this was actually an interesting case where the original bridge deck was made of shallow arches in masonry. And in order to increase the load-bearing capacity of the bridge, it was decided to remove the old bridge deck and replace it with a very lightweight prefabricated UHP-FRC bridge deck that is stitched to the steel structure with in situ joints, like you see on the picture on the right. This allowed to remove several thousand tons of self-weight from the structure and therefore to increase the load-bearing capacity for modern traffic loading. So again, it's a combination of good engineering, the right system technologies and solutions, and the ability to execute the works to a high safety and quality standard that really delivers best for project value. And with this, I want to close this short presentation. And I thank you again for the opportunity to show some of these international examples.
So thank you very much. So you explained us a little bit more about the replacement of the deck of the truss bridge, because we have a lot of those bridges in Vietnam that need attention right now.
Yeah, I think you have quite a number of bridges of that generation.
Yeah.
And I think here on this bridge, there were a couple of things that required intervention. First, it was a general retrofit, so a durability repair. You see recoating of the steelwork, localized repair of corrosion on the steelwork, which is obviously something that you typically try to do when you do such an intervention. But then here, particular was, unfortunately, you don't see it here on the photo, was the bridge deck, which you have transverse steel beams. And then between the steel beams, you have these masonry shallow arches or voûtes spanning between individual steel beams, and then a very low quality concrete road deck on top. And over the years, obviously, the asphalt has been replaced, resurfacing has been done, so there was also probably some weight added to it. And then I think here the objective was to upgrade that bridge to the current road design standards with increased truck loading. And this was then done by removing the entire bridge deck. So this was conventional breaking out. So there was you can see a little excavator like the one here with a jackhammer that was used to break out the existing deck. Remove this. Then you have precast panels, which were precast in a factory using UHP-FRC. They're very thin. I don't remember the exact dimensions, but imagine maybe something in the thinnest section, maybe 10 centimeters. And actually they were already fabricated with the required crossfall. They were placed on new or reinforced transverse steel beams, because the old steel beams had suffered some corrosion. So the new steel beams implemented. These steel beams had some Nelson studs welded to them to form the joints between the panels. You have some starter bars going into these joints, and then you see here the in situ mixing and application of ultra high performance fiber reinforced cementitious material to cast the in situ joint to form a monolithic connection. And at the end, you have asphalt over the top. Again, with this material, you don't need waterproofing. So it was a very nice solution to.
It's impressive. We have a similar one in Vietnam, that is Thăng Long Bridge. is 2 years ago, and in the future we have to replace quite a few those kind of bridges.
So I think this type of solution is
Yes,
maybe interesting for these bridges as well. Yes.
And another question about, let's say, to replace the existing cable in cable stay bridge. How do you, let's say, calculate the cost and the procedure for those kind of bridges? For example, because you don't need to replace all the cable, you just have to replace a limited number of cable. So how is the pricing? How do you, let's say, proceed that project with the client?
Yeah, I think it depends a lot on what is the reason for the replacement, right? That if it's because you have corrosion or some fatigue damage to the cable, I think the first phase, which is very important, is a thorough inspection. And I showed a few methods, but for example, we did not talk about the possibility to use magnetic flux measurements to detect directly steel breaks, so either corrosion or fatigue breaks in the free length of the cables. You can obviously do visual inspection of the anchorage components to establish the condition of those. You can also use ultrasonics to test, in some instances, the condition of the wires or the strands inside the anchorages. So I think it's really down to, you need to have a thorough inspection regime to determine which cables you need to replace. A bit different is it obviously if you need to replace cables because you want to upgrade the load-bearing capacity of a bridge and you want to substitute existing cables with larger cross-sections. And then most of the cases that we have been involved with, you have to do this under traffic, which means you can, again, it all depends on the original bridge design, but in many cases you cannot just take out one cable and allow full live traffic on the bridge. So that is then, and you see actually the photo here, the aerial view of that bridge. That's the bridge in the US, in Louisiana, where the cables have been completely replaced, and we use temporary cables in order to take over the load and then detension the existing cable. And the cable here in yellow, the bridge there, this is a bridge in Germany we're currently working on. This in this case is actually deconstruction, but also with a controlled detensioning. So I think the question is not easy to answer, how much is the cost, because it depends a lot on, first of all, what is the objective and how many cables you need to replace.
So thank you very much for the very intensive presentation about the experience in the many countries with many kind of bridges. And we do hope you come again, and we invite you to visit several typical Asian bridge in Vietnam. And can have visual inspections, so to consider, let's say, how to treat those structures early before the treatment become too much expensive.
Thank you very much. I think you have a great range of bridges here in Vietnam, and certainly looking forward to hearing more about them. Thank you very much.
Thank you. And currently, we're planning to build 5,000 kilometer motorway from the north to the south, and then we have a lot of, let's say, long-span bridges along the coast.
Yes. Mm-hmm.
So the experience will be very helpful to Vietnamese infrastructure. Thank you very much.
Very good. We are here in Vietnam. We are always available for further questions and discussions. Thank you very much.
Thank you very much.
Thanks.
Congratulations for 30 presentation in Vietnam.
Thanks.